Okay, hello, and we'll try this again. I'm a little concerned about the sound quality that we might have here, but we'll just go ahead with it. I've got another example to look at for you, and it is a regenerative cycle, and it's another complicated one, meaning that it's got at least two feedwater heaters. But this closed feedwater heater complicates the cycle quite a bit, because as you'll recall, that the condensate from the closed feedwater heater, we're going to bleed steam from the turbine and use that to preheat the feedwater that's coming from 4 to 5. And in so doing, we're going to condense this steam in the closed feedwater heater, and we've got to do something with that condensate. It either needs to be pumped forward to the next highest pressure level, which in this case would be the boiler pressure, or it needs to be sent back through a pressure drop to the previous lower pressure level. So in this example, in this problem, that condensate is passed through a valve, which is described as a throttling valve, and that condensate is flashed through the valve and dumped into the open feedwater heater. So there's the two features of this problem then that are a bit different. We do have the closed feedwater heater that we haven't seen before, at least in an example, and then there's an open feedwater heater here. And this open feedwater heater control volume, I think immediately you can see that the balance equation for this open feedwater heater is going to be different, because it has 4 streams entering into it instead of just 4 streams emanating from it. We have 3 coming in and 1 going out. The open feedwater heater that we saw before only had 2 streams coming in and 1 stream going out. So let's take a little look at the specifics of this cycle. He says that it has steam supplied to the turbine at 12,500 kPa and 550 degrees C. The condenser pressure is at 10, and there are 2 extraction pressures, one at 800 kPa, the second one at 300 kPa. He does tell us explicitly that the feed water is heated to the condensation temperature of the extracted steam in the closed feedwater heater. Okay, what does that mean? The feed water he's talking about here at state 4 at this point is heated, that's at state 5, to the condensation temperature of the extracted steam in the closed feedwater heater. So what it means is the extracted steam is going to condense, and that condensation temperature is the temperature that 5 reaches. And I mentioned this the other day as we discussed closed feedwater heaters, that would ideally be the maximum possible condition that we could reach. In other words, that this temperature 5 could attain the same temperature as the condensation temperature. So what it's saying here is that the temperature 5 is known, and that temperature is equal to the saturation pressure, the saturation temperature corresponding to the pressure 9. The condensation temperature is the saturation temperature at this pressure 9, which is known. So we know temperature 5 from that statement. Then he says that the extracted steam leaves the closed feedwater heater as saturated liquid. So he's further telling us that the extracted steam leaves the closed feedwater heater as saturated liquid. So he's specifically telling us that state 6 is saturated liquid, and then he says that it is subsequently throttled to the open feedwater heater, and that's what he's showing here, this throttling process 6 to 7. I hope you will recall from Thermo 1 that a throttling process, and you can review chapter 5 as necessary, throttling process is one that has a constant enthalpy. So we have H6 equals H7. That's what he's basically telling us there. and then so I think that's all that he's told us about that closed feed water heater. So we're supposed to draw a TS diagram, determine mass flow rates to produce 250 megawatts of power, and the thermal efficiency of the cycle. Okay, I have put together the TS diagram for this, and I apologize we won't be able to look at them concurrently, but I'll switch back here. But bear in mind that we're going to have 1, 2, 3, 4 pressure levels in our TS diagram, and typically entering into these pumps is going to be saturated liquid states. In other words, the ideal Rankine cycle, we're going to fully condense this condensate to saturated liquid and then pump it up to state 2 isentropically. Then we're going to extract just enough steam so that when we mix this together, 2 plus 7 plus 10, that we come out again with saturated liquid at state 3. So states 1 and 3 are going to be saturated liquid. We have to know that in this case, but he did tell us explicitly that the state 5 is not saturated liquid, but rather it is at a temperature 5 that is the same as the condensation temperature of the steam in the closed feed water heater. Okay, so we've got all those points. We know the temperature going into the turbine, and furthermore, he did not say anything about this turbine's non-adiabatic conditions, so we have an isentropic expansion. That means entropy 8 equals entropy 9 equals entropy 10 equals entropy 11. So I've pretty much described this TS diagram that you see, and hopefully that all makes sense. 1 to 2 is isentropic pumping, 3 to 4 is isentropic pumping. Remember that state 3 is in the open feed water heater, where we mix states 2 and 7 and 10 to get state 3, and then 4 to 5 is heating in the closed feed water heater, and I'm trying to show the temperature 5 at the same level as the temperature 6. I think they don't quite line up there, but it's the best I could do on the chart. So with temperature 5 equals temperature 6, then we have heating in the boiler. 5 to 8 is the boiler process, and then the isentropic expansion 8, 9, 10, 11. The only thing that's a bit of a new wrinkle here, I think, is that we have this throttling process, and I've shown this throttling process as a dashed line, as we would do, to indicate that the precise state path from 6 to 7 is not known, but we do know that it is going to occur at constant enthalpy. So that is actually an H equals constant process, even though I'm unable to show that on this TS diagram. So the enthalpy is constant from 6 to 7 because of the throttling. So this is the TS diagram for this problem. Okay, and I've got to jump on the analysis over here already for you, and I'll try to walk you through what I have come up with. First of all, here's all the given information, and it needs to be mapped out carefully because if you make a mistake in here, then using the formulas down below obviously is going to give you poor results if you have the wrong value associated with a particular state. But these pressures, again, just all of the states that are on the same line in the TS diagram, that is on the same pressure line in the TS diagram. 4, 5, 8, they're all the same pressure. 2, 3, 7, 10, they're all the same pressure. 6 and 9, they're the same pressure, and 1 and 11 are all the same pressure. And likewise, you can see that from the hardware schematic. Everything that's connected to the same device where they have common communication of fluids, then they're all the same pressure. What does that mean? Well, everything here, 3, 7, 2, 10, that's all the same pressure because they're connected together through this open feed water heater where all those streams are in contact. On the other hand, if we look at the closed feed water heater, the pressures 9 and 6 are going to be the same because they are connected through a pipe. But the pressures 4 and 5 are also going to be the same, but as each other, but different from 6 and 9 because they're not mixing. That the flow through 4 goes over this pipe and then comes out into another pipe. So pressure 5 equals pressure 4 equals pressure 3. Pressure 5 equals pressure 4, and pressure 3 is equal to pressure 2. Anyway, all that is hopefully captured in the list that I'm showing you here. So I've tried to identify most of that. I guess I didn't pull this out, that this is actually referencing the previous state. Okay, so let's see what we've got then. The other given information here was that the temperature at state 8, that's going into the turbine, is superheated at 550 degrees C, and the temperature coming out of the closed feed water heater is the same as the, what do you say, the condensation temperature of the steam in the closed feed water heater. And I've calculated that using the function, but this is just to look up in your tables to find the saturation temperature corresponding to the extraction pressure of 800 kPa. And then it was also given that the state 6 was fully condensed coming out of the closed feed water heater. That extracted steam is fully condensed. So I've indicated that by showing the X6 is equal to 0, but it just means it's saturated liquid. And then I just wrote here in words, I couldn't find a better way to do it at this point, but H6 equals H7 because of the throttling process there. So when we come up with these enthalpies, we can just set those equal once we find H6. H7 is going to be equal to that. Okay, so going back to our hardware, remember we always want to start the analysis with the feed water heater that is closest to the boiler, and so in this case that's this closed feed water heater. So let's see if we can get through this closed feed water heater analysis, and then maybe we'll take a break. So what do? We put this control volume on that closed feed water heater. Anything that crosses the control surface needs to go into our first law equation. Again, the assumption is there's no external heat transfer. There's obviously no work done within this control volume. 4, 9, 6, and 5 are mass flow rates crossing the boundary, and they have energy flows associated with them. So we have Y, the fraction in this branch is Y times H9 is coming in, plus what's the flow rate in this branch right here? Well, it may not be obvious. One way to look at it is that going into the boiler, this is the full flow rate. That's our reference flow rate, M dot boiler. So this is equal to 1, and since what's going into 5 has to equal what's coming from 4, we know that flow rate fraction 4 is equal to 1. The other way we could find that is to go back to the open feed water heater and look at the conservation of mass on this and add up the flow rates that we have. 1 minus Y minus Z coming at 2, we have Z coming at 10, and we have Y coming from 9, 6, 7. So when we add those together, 1 minus Y minus Z plus Y, that all adds up to 1. So we have a full flow rate going 4 and 5, that is, the fraction is equal to 1. So we have Y times H9 plus 1 times H4 is equal to Y times H6 plus 1 times H5. And I've tried to write that in maybe a little bit different way. I've said Y times H9 minus H6 is equal to 1 times H5 minus H4. In other words, this is the decrease in enthalpy of the condensate, and this is the increase in the enthalpy of the feed water. So I've gone through the usual hijinks here to try to come up with these state information. We start with the state we know, saturated liquid coming out of the condenser, and we find its entropy and enthalpy, and then I'm going to use the compressed liquid data, that is the functions in Excel. I'm going to find that H2 is given by the entropy at state 2, which is the same as the entropy at state 1, and the pressure at state 2. So that's the isentropic pumping process from 1 to 2. Then state 3, we know that just enough steam is extracted to make state 3 by design equal to saturated liquid at pressure 3. So we just look that up in the table. We find the corresponding entropy, because this process 3 to 4 is going to be exactly the same as the process 1 to 2, isentropic pumping. So now I'm going to use the fact that we know the pressure and the entropy of this compressed liquid. We can calculate the enthalpy H4. And then finally this H5, which is what's exiting that closed feedwater heater, state 5, that's the one where he gave us the temperature. This is also in the compressed liquid region, and we can see this on our diagram. And so we can use the compressed liquid tables to find the properties of that. Now, it's an interesting question, and you should be aware, if you're working this by hand, how would you find that property if the compressed liquid table does not contain an entry for 12,500 kPa? I think it actually does, the table in your textbook, so I think you could look this up. But the standard assumption about compressed liquid, or approximation for compressed liquid, is that the enthalpy is a strong function of the temperature, and so we would look up the corresponding temperature of the saturated liquid. And then add the overpressure or extra pressure V delta P term that's associated with the increase in pressure. So I won't go through that here, but just to mention that working by hand, and again you can reference Thermo 1 section. I believe that's going to be either in chapter, probably in chapter 3 of your Thermo 1 book. Okay, so let's proceed ahead. What are we missing here? We've got 4 and 5. Do we have 6? How are we going to find state 6? State 6 is fully condensed. He told us that, so we just need to look that up in the table. So H6 is just equal to HL, and we know that as a function of the pressure, and that pressure is P6. And then we need to find state 9. What is state 9? That's a good question. State 9 is the extraction. So we have to find that from the isentropic expansion through the turbine. So we first have to find state 8. So we look up state 8 and its entropy, and then we'll use constant entropy to find state 9. So H9 is equal to H as a function of the pressure and the temperature, and the pressure we know is P9, and the temperature we know is, I'm sorry, I've got this wrong. I need to put P8 and T8 and then change my label. We're doing state 8 first. There we go. And we need to find the corresponding entropy. And there we go. And finally, put some labels on these last few. that we made, I think we'll be able to calculate H9 from the pressure and the entropy pressure 9 and entropy 9 is the same as entropy 8. So S9 equals S8. Okay, so now we know all these states, and we should be able to calculate that fraction. So what is that fraction? Y fraction, I'm going to need this, and ultimately I'm going to need that, so I'll go ahead and make that. So I've lost the formula here, but y is going to be 5 minus 4 divided by 9 minus 6. So this is equal to H5 minus H4 divided by H9, oops, H9 minus H6. Did I get that right? Yeah, 9 minus 6. Very good. So the fraction is 7.5%. If we wanted to show that in a percentage, we could do that, maybe with a couple of decimal places, and maybe we could clean these up a little bit. A little bit too much precision on these numbers. Okay. Alright, so that's it basically to analyze the closed feed water heater in this example. We'll take a break and I'll come back and calculate, do the analysis on the open feed water heater for you, and maybe finish this thing out.